In this video, we will get to discuss organohalides, chapter 10. Organohalides are compounds that they contain halogen somewhere. You can have compounds like this. I have a benzene ring with the halogen somewhere, and then another alkyl side chain, so that will be organohalide. Now, what is an alkyl halide? Alkyl halide is when you have an alkane and you have attachment directly to one of the carbon atoms. You can have attachment of bromine, chlorine, etc. That will be an alkyl halide. And then another particular case are the allylic halides. Allylic halides is when you have a chain and you have a double bond somewhere, and then you have a halogen like bromine attached to the carbon atom that is immediate neighbor to the double bond. And so there we have three different kinds of organohalides. That will be an aromatic halide, this will be an alkyl halide, and this will be an allyl halide. First thing that we need to take care of is the nomenclature, the naming of the compounds. So we will keep it simple. We follow pretty much the same rules of nomenclature that we have learned before. And I will illustrate this with this example. So first, in this particular alkyl halide, we need to determine which one will be our carbon number 1. If I number from this end, 1, 2, 3, 4, the bromine will be in carbon number 4. But if I number from the other end, 1, 2, 3, so the first substituent, the methyl group in this case, will be in carbon 3. So I prefer that option. So I will have to indicate that in my longest chain, that is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have a bromine in carbon number 6. So that will be 6 bromo. Then I need to respect the alphabetizing the groups. In carbon number 5, I have 2 fluorines. So it will be 5,5 difluoro. And then in carbon number 3, I have a methyl. So there you will have the complete name. It will be 6 bromo, 5,5 difluoro, 3 methyl nonane. So that will be the complete name. Properties of these alkyl halides. Well, because the halogens are more electronegative than carbon, you should expect that there will be a polarity in those bonds. Actually, you can see that no matter which halide you are dealing with, whether it's a fluoride, chloride, bromide, or iodide, in all cases, the dipole moment is not very different, actually, but in all cases, the dipole moment is greater than 0. How about the bond length? The bond length, you can see that as we go from fluorine to chlorine, bromine, and the iodide, so the bond length gets longer and longer. That is only natural because the atomic radius of chlorine is bigger than the atomic radius of fluorine, etc., right? So it's only natural that. As far as the bond strength, you can see that as you move down from fluorine to iodine, the bond strength gets weaker and weaker. So it's much more difficult to break a carbon-fluorine bond than breaking a carbon-iodine bond. We will get to see that in chapter 11 when we analyze the nucleophilic substitution, that is going to have some influence in the rate of the reactions. So how can we make alkyl halides? Well, we have already learned one method way back in chapter 6 or 7. We learned that if you have, for instance, a molecule like ethane, CH3, if you react that with chlorine in the presence of light, so then you can get chlorination of this ethane, and you can form 1-chloroethane. Notice that here, because the molecule is so small, it doesn't really matter if I put the chlorine in the carbon atom on the left or the carbon atom on the right. In both cases, I will get exactly the same thing. But then now, once we go to 3 carbon atoms, propane, there the situation gets slightly more complex. Let's say that I'm reacting that with bromine in the presence of light. I will get a mixture of 2 compounds, right? Because I can put my bromine in the first carbon atom, or I can put the bromine on the carbon atom in the middle. So I can get 1 bromopropane, or I can get 2 bromopropane. So which one of those will form in higher proportion? That is going to be the matter of discussion in the next few slides. So where are we? Okay, there I advance to the next slide. So remember that the mechanism of the reaction involves a radical chain reaction. So you have an initiation reaction when you have the splitting of the chlorine. Then you have reaction of the chlorine with the alkane. In the slide that I'm showing now will be the reaction with methane. And if you have enough chlorine, you can go through additional chlorinations. So you can go, once you have formed chloromethane, you can go through a second chlorination to form dichloromethane. That is the same solvent that you use in the lab for running chromatographies, right? Or if you go through yet another chlorination, you can form chloroform. Chloroform also is a very, very well-known solvent. Or you can form even carbon tetrachloride. Nowadays, this is not a very popular solvent because it's rather toxic. So it is chloroform. Chloroform is not very healthy to use. So then here you will see that we will have in OW some questions about how many different halogenation products can you expect for a given substrate. So let's practice this here. So let's say that I have this compound. What is the name of this compound? It will be 1, 2, 3, 4, 5. And so this is a pentane. So it will be 2,2,4 trimethylpentane. So how many different products can I form here? Well, so here my advice, be systematic. As you go 1 carbon at a time, analyze. So I can put my bromine in this carbon, right? Notice that I will not propose to put it on that carbon there, right? And this carbon there, because if I put it there, it will be the same product as putting the bromine on the other methyl group, right? Those two are exactly equivalent. Then I can put my bromine on that carbon atom. That will be different. What is the relationship between this structure here and that structure there? Well, they are constitutional isomers, right? Constitutional isomers. Then where else can I put it? Well, I can put my bromine on that carbon atom, right? And then where else can I put it? Can I put it there? Sure not. I cannot put it there because that carbon atom doesn't have any hydrogens, right? and there are no hydrogens there. So I cannot put my bromine on that one. So forget about that. And the other possibility, I can put it here, right? So those will be all my possibilities. I will have 4 different constitutional isomers with the bromine in this position, or in that position, or here, or here. And then now we can have a follow-up question. And how many of these monobromination products can be chiral? So how many chirality centers I have in this first compound here? Well, that carbon atom here, right? That carbon atom there is chiral. So that means that I can have 2 different flavors for that. I can have the R configuration. Doesn't write very nicely, the yellow. I can have the R configuration, or I can have the S configuration. How about here in the second compound, in this one here? Well, here there are no chirality centers. So I have only 1 constitutional isomer, right? Without stereoisomers. How about here in the next one? In the next one, this carbon atom here will be chiral, right? That one was chiral here. This one is chiral there, right? So again, I have the possibility of R or S configuration for this other compound. And then finally, for this one here, I have only 1 stereoisomer, just 1 constitutional isomer without the possibility of stereoisomers. So the answer to the initial question, how many different constitutional isomers can I get? The answer will be 4. You get 1, 2, 3, and 4, right? And how many of those are chiral? Constitutional isomer 1 is chiral, and I can have 2 stereoisomers. Constitutional isomer 2 is also chiral, because I have that carbon atom chiral, and it will come in 2 flavors, R or S. Okay, so I will stop here and we will continue later.